We're very excited because we have a lot of great speakers this year, and we're very committed to the idea of the Colloquium. And part of the idea of the Colloquium is that you become exposed to ideas and research that you wouldn't encounter otherwise. So it might be outside of your area. It's a chance to broaden yourself, to expose yourself to a lot of different research areas. So we have a special privilege today to hear from my friend and colleague Lei Li. So Lei finished a PhD at CMU's School of Computer Science, with which many of you will be familiar, in 2011. He did a postdoc at UC Berkeley, and he went on to do a number of remarkable things in industry and then in academia. He was, for example, the founding director of ByteDance AI Labs, and as part of his association with ByteDance and so on, he's led the development of software that serves billions of people every day. So he's somebody who makes a real impact through his work. He also was a tenured professor at UC Santa Barbara before coming here, and we're lucky to have him. And he's going to talk today about a way of having an even greater impact through machine learning and NLP-related techniques, and that is through molecules and through biology and molecular design. So please join me in welcoming Lei Li.
To make more impact together with all of you, with all our fellow researchers and students, to go from just NLP to other domain of the sciences. So today I'm going to talk about how we use some of the technology we developed for NLP and extend that and design algorithms that are suitable for molecule design. So, how did the story start? That was 4 years ago. I was attending a conference in February in the US. So at that time, the COVID hasn't hit yet. So I was having the luxury to attend in-person conference, two important in-person conferences. Initially at New York, the AAAI was talking about machine translation there. And immediately after that, I attended another conference in MIT in Boston about drug design. And surprisingly, people were talking about these models that are very similar to what we were using for text generation and machine translation. And then boom, COVID hit. Right after I attend the conference, I received an email from the organizer saying, okay, one of the participants actually got the COVID. I was very worried about that, but luckily I didn't get it. But that was a story how I started working on molecule design and drug discovery. I really found, okay, our AI algorithm can really make an impact in those domains. Of course, I'm not really a pharmaceutical researcher or chemistry researcher, so my knowledge about the chemistry might be wrong, so correct me if I'm wrong. I'm trying to be precise. So we know that large language models have driven the productivity of everyday work, translation, summarization, editing, or even writing the email, or even more chat about the questions and making recommendations. That's great. We are very familiar with that at the LTI. And this generative AI also drives imagination. This is an image actually I generated using OpenAI's DALL-E model with this specific prompt using generative AI for protein design. So this is a generated image. Pretty nice. Well, how about molecule? The central question here is, well, there are a lot of questions to ask about a molecule, but the particular question we are interested in is, can we use generative AI to design molecules with a specific function, with a desired function, which we want? We can use this molecule, for example, for medicine as a drug, or vaccine, or using it as an enzyme to speed up, accelerate certain reactions. I will talk about this more later. To be used as a biosensor, for example, to mark certain target in our human body or in the cell, or to manufacture new materials. Well, there are already a lot of work in chemistry, in biology, to design this through lab experiment, through trial and errors. Of course, that takes a lot of time, and it takes a lot of expertise as well, labor intensive. So our goal is to use this AI algorithm that can accelerate at least a certain part of the process so that we can make it more efficient and faster. So you may wonder where I jump from NLP to this molecule. Are there similarities and differences? Yes, there are a lot of similarities. Actually, that's one of the main reasons I jump, and I also find it comfortable to work on these topics. I hope you can get the same sense of feeling after the talk. So there are actually three perspectives we can think about in terms of molecule design. So I give you some quick summary here. So in terms of modeling, how we model them, how we model the language, and how we model the molecules, there are a lot of similarity. Of course, there are also some differences, which I will also talk about. In terms of training these models, there are even greater similarities. There's a direct training, cross-entropy, contrastive learning, reinforcement learning, etc. Similar ideas. In terms of generation, decoding, where we do a lot of decoding for text, there are similar decoding algorithms for molecules. So well, let's start with the first one. So in terms of the how to represent the data here, well, we have text. We always decompose them into sequence of discrete tokens. In molecule, so this is one example here. If you recall the name, remdesivir. So it's an early drug for the COVID. To the molecule structure, to the molecule. So you can exactly recover the bond there. Okay, and this one, you can see it's also a sequence of discrete tokens. It's pretty much similar, it's just a different vocabulary. So we can also tokenize the sequence in the same way as if we tokenize the English text, and then train a model for that. Well, there's also some difference as well. In particular, for protein sequencing, when we are talking about the protein are fundamental building blocks of life. They provide important biological, chemical functions. These sequences are composed of amino acids. There are 20 of them. So like these ones are example. So it will be represented like this. So it's a sequence of discrete tokens. And at each location, we have one token from the 20 vocabulary. And the difference is, well, in terms of length, it's much longer. So if we think about the length of these protein sequences I put here, that's a frequency or count of the number of proteins in a database called PDB, Protein Data Bank. And we can see there are even sequences longer than 1,000 tokens. and even longer. So that's much longer than the usual sentences we are processing for NLP tasks. And we have very good tools to process these discrete sequences. For language, we have BERT, GPT. Similarly, for these chemical sequences, there are similar models called ESM, ESM2. Those are similar to BERT. I will introduce in a minute. ProGen, which is pretty much protein version of the GPT. So we can borrow the same idea from NLP. So this is one of the two protein language model people developed at Meta. So the idea is similar to BERT. We have sequence. This is a protein sequence. Each one is just one amino acid, or we call it the residual. We randomly mask some of them. We put mask token here. And then we process through a transformer encoder. And at training time, we just predict those mask token. Okay, so we try to recover those using the exact same usual entropy, usual training loss we use, cross entropy, to predict predict the tokens here. And it's very effective in practice. So people have trained two versions of it, ESM and ESM2. So this one is even published in Science last year. And the algorithm is, and in terms of the algorithm and model architecture, it's pretty much the same as BERT. And similarly, another group from Salesforce, they developed this autoregressive language model using transformer decoder. Again, we have the same protein sequence. We're trying to use this transformer decoder to predict next token here, next residual in the sequence. And using this, we can then generate sequences. So this causal language model is for generation purpose. We can actually use it for generation. And well, if you are taking my multilingual NLP class, you will notice that when we use transformer for multilingual translation, we will add a language tag here, right, in the beginning to indicate the target language, source language, and target language for the translation. It's similar for the protein sequence. So we can add a tag to indicate the protein family, that's category to indicate the function of the protein. And at generation time, we provide that tag. Then we hope to generate new proteins belonging that category with the same function. Okay, so that's about the sequence. And well, beyond sequence, we also have structure. So for text, there's a tree structure. We have like different kind of trees to represent the syntax for text. It's not as popular now after transformer, but before transformer, when we have LSTM, there's a tree LSTM to encode the sentence and also generate the sentence together with the tree. So for molecule, it's not a tree, it's actually a graph. So we have two-dimensional molecule graph. It's a discrete graph. Each edge here is a bond. And then we can use a tool to represent the information in the graph. So a class of the most popular tool is called graph neural networks. So this is how it works. So we have molecule here, and we can represent as a graph. So we compute representation for each of the node. The representation is just a vector. And we want the representation to contain knowledge about the graph. So how we compute it? We compute, the basic idea is we compute this vector representation based on its neighbors, based on its connecting neighbors. So this one, for example, this carbon atom will receive information from its neighbor, its oxygen, hydrogen representation. And then once it's received the information and use a neural network, this is just some neural network we can design, can be multi-layer perception, for example. And then we aggregate that information and combine it with the information it has from previous iteration, and then aggregate them together. So that will be our computed representation for next layer. And we go through this process for many layers, and then eventually we get the final representation for each of the node. And then we can make predictions, or we can make generations based on this. So this has been used in practice for many years. And there's a further development on this. It's not just a graph of atoms. We can also design this graph hierarchically. So it's we can have a graph of fragments if we break the molecule into pieces of fragment. And we connect the fragment together. So we have graph of graphs. And similarly, we can compute the representation here for each of the fragment, then compute the aggregate representation for each fragment node, and then we can compute the final representation of the whole graph. Okay, well, once we have this graph representation, what can we do? Well, there was an algorithm before for text. We can use an iterative editing idea to iteratively improve the generation quality of the text. So we can borrow the similar idea to molecule generation. For example, this is one work we did before using iterative editing based on this fragment graph. So the goal is to generate some molecule satisfying certain property. I will talk about the properties later, but at the moment, you just think of this as an objective function we're trying to optimize. So we will start with some initial fragment, and then we can do two operations. We can either add one fragment to existing one to form a new graph, a new molecule, or we can break down some of the bonds in existing molecule, and then delete or remove one fragment, and then we get a new molecule as well. So through these two procedures, we will arrive at a new molecule, and then we can evaluate the quality of this new molecule, whether we will keep it or we will go back to the previous and do iterative editing again. So through this iterative process, hopefully in the end, we will get much better, higher quality molecules. Okay, so we've talked about sequence and structure, discrete structure. There's also continuous structure for molecules. That's unique for molecule. So this is corresponding to the geometry or coordinates of those molecule atoms and the residuals. So the usual way to represent the geometry is either we represent a matrix of 3D coordinates, or we represent a matrix of the angles between these atoms and the residue. Of course, for protein, it's slightly more difficult because protein has some secondary structure and 3D ternary structure and even more higher order structure. Well, how to model geometry? As here, again, we have a graph, but it's no longer a discrete graph. Each node actually has connectivity to the neighboring edge, neighboring nodes, but also has coordinates. We want to make sure the representation for this graph and nodes, they preserve certain kind of invariance under the geometric transformation, such as translation, rotation, and the mirror. So let's say if we have an object in the space, if we move it, it's still the same object, right? Our algorithm should recognize, so we should have the same representation for the same object, no matter how we move it in the space or how we rotate it. So that's the key idea. And for that purpose, there's a method called equivalent graph neural network. The key idea is when we represent each of the node here in the graph, we also take consideration of their coordinates. And we make sure the transformation as we go through past the representation through the network, their representation keeps geometry invariance. So they are invariant under the translation and the rotation. And this particular design, for example, can ensure this invariance. Okay, now we have all the building blocks for the data representation and model. So I'm going to talk about the specific problems for molecule design. There are roughly several categories. There's small molecule design, protein design, and ion design, and other macro molecule design. For small molecule design, it has different purposes. So the particular purpose I care about is for drug design. So we want to design the small molecule to cure a certain disease. For some disease, most of the disease actually, we are studying the disease, trying to find the target for the disease, so that we can develop the drug molecule to targeting that particular target. A target is usually a protein, and to make the drug effective, we have the molecule has to bind to the target protein to make it effective. So this is target-based drug design. And of course, we also want to ensure that the molecule has certain desired properties, such as low toxicity. It shouldn't be toxic to human body. It should be synthesizable in factory or in lab, right? If a compound, we find a new compound, if it's too difficult to manufacture, then we can't get that drug. And it should look like drug. There's a score developed in chemistry community called drug likeness, specifically QED score. So it will tell how likely, it's not a perfect score, but it's an approximation. It's like the blue score we used for machine translation. For protein design, there are also different purposes. There are enzyme design, protein binder design, where we want to design a protein that can bind to a target protein. There's biosensor, so we want to design a certain protein that can, for example, exhibit green light under certain condition. Antibody design as well. There's RNA design, for example, RNA for vaccine purpose, for other purpose as well. So for the remaining time, I will mainly talk about the protein design. We have some work on the small molecule design as well. So if you are interested, you can look through my website to find the paper. So let's see, for protein design, there are actually three approaches. I roughly categorize into three categories. The basic one, which many of you might find the algorithm familiar, is sequence-based design, sequence-based generation. And then we go from sequence to the structure. We can use the structure to guide the generation, either using the secondary structure or use a full 3D structure that's called inverse folding. Or we can also use some partial structure, for example, the surface of the protein to design the whole protein. And we can go further to combine the two together. We can have a sequence and structure co-design by considering sequence and the 3D structure together. Okay, let's start with the first one. So for sequence-based design, well, our goal is to generate or design a protein sequence satisfying certain property. Here, how we represent the property, where we use a scoring function called fitness score to indicate the function. One specific case of this fitness score is, for example, the green fluorescent protein. The score actually represents the intensity of light under the condition. So whether this protein will send green light out or not, and how intense it is. So this can be trained using lab measure data. So you can view this as a metric function, basically. And once we have that, we can model this generation problem using Bayes' rule. So we want to maximize the probability of X. Here, X is the protein. We want to maximize the probability of getting this high quality protein given certain threshold on the fitness score. So S represents the threshold on the fitness score. And then we can decompose this into this form. We have the first part, which is corresponding to the raw data generation probability on the protein. It has nothing to do with fitness. And the second part is basically a fitness function. Given a protein, given any protein, can we tell the fitness score? And at inference time, we are given a protein family tag, so given an indicator, and to the generative model, and then we generate the sequence. And then we use the fitness scoring to either filter the good high quality protein, or we can even integrate that fitness function into the generation, guide the generation procedure. So this is pretty much similar to what we were doing for NLP. So there's a conditional, for example, conditional VAE model that is conditioned on the target score. And so the reason why we formulate in this way, instead of directly train a conditional model of the target protein sequence, is we have limited data for each category. For example, in green fluorescent protein, we only have a few. So it's not enough to train a direct conditional generative model. But instead, if we decompose, then this part can be trained separately with lab data. That's the discriminator. And this part, we can combine all the protein data to train a raw protein generative model. And we have a lot of data for that from a protein data bank. So this is one framework to train the model. It's basically a variational autoencoder. We assume the data, the raw protein, is generated from multivariate, standard multivariate Gaussian distribution. And then we have a transformer decoder, because here we only model the sequence. So we can use a transformer autoregressive decoder to generate a sequence like this. Then from that, from the ground truth sequence, we can further going back using transformer encoder to encode the sequence into a vector representation. And this will be the posterior distribution. And the training loss here is we will bring this posterior distribution closer to the prior distribution using KL divergence, together with a reconstruction error there. So that's the same training loss we use for text using the variational autoencoder model. Now, one specific challenge is this works for some scenario, but it doesn't really work. The success rate is really low. Here's the issue with the basic variational autoencoder. So if we're training a model, raw model or raw generation model, it's like this. It's in blue curve. This is just for illustration purpose. And from this, we want to find good proteins. So x-axis indicate the fitness score. The higher, the better. So we set a threshold here. All the proteins that are generated on this side are good. And you can immediately see the percentage, the chances that you are generating these high quality proteins are very low, right? This right tail is very low. So you have very low probability to get high quality proteins. Well, how to deal with that? We propose a method called ESM Pro. The key idea is so we have raw data generation probability, and we have high quality ones here. We are training another approximate distribution, a generation distribution, using a variational model to approximate this right tail, so that this one, once we train it, we can directly generate it. And then by setting a threshold on this one, this orange one, it will give us much higher probability of getting high quality proteins. Well, once we have that, we can set up a mathematical formula for the training objective. For example, here we are using the KL divergence between this is prior high quality conditional probability for the high quality proteins. And this is a variational, this is an approximate one. And we are using the KL divergence here. We are trying to minimize the KL divergence or maximize the negative KL divergence here. For this purpose, we can train two separate variational autoencoder, one for the prior, one for the variational one for the actual proposal which we want to generate from. So this is the full model, but we are not going into the details here. And one important feature for this model is, well, this is not enough. So we need to add additional combinatorial feature to make it even more effective. And this is something our NLP people are very familiar with. It's called Markov random field. So a Markov random field basically captures the correlation of any pairwise correlation of the tokens in a sequence. So we can learn it separately from the data. And once we learn that, we can incorporate, those are the weights learned in this model. And once we learn that, we can incorporate this feature into our decoder, into our generator, so that we can, well, this is the learned weights from the Markov random field. We add that to the embedding of the residual, each residual, and we take the aggregate embedding as a new input to the decoder, so that this decoder will know something about the current input residual, or the previous input, previous generated residual, and also correlation information of the current token to all previous, all neighboring, all the context tokens. Then it will be more likely to generate natural proteins that look like these natural proteins in our database. So once we have that, we can generate much higher quality proteins. Well, how does it work? We measure the fitness, average fitness value here. The y-axis is the fitness score. The higher, the better. And these are different algorithms. And in particular, there's one called ESM search that's based on the ESM, if you remember. This is a BERT-based model. We can have a BERT model and have an initial sequence, and we randomly mask that, and then we predict the masked token and trying to search for the best using the fitness as a filtering function. So well, on 8 data set we tested, it turns out the ESM Pro gives us a much better, much higher fitness score. And what about diversity? Where in text, we care about diversity. We want to generate a novel or new different text. That's not really just copying the training data. So in molecule, it's the same. We want to design new proteins, novel proteins that are not in our training data. So we compare the similarity between the generated protein versus the one in our training. So this is a well, this is a diversity score actually, just measuring how different among the generated one. And the higher is better. We also have a novelty score. So this is comparing similarity between our generated proteins versus the ones in the training data. Again, the higher is better. So if you are curious about the actual protein generated by this algorithm, so this is one example. This is one real case we designed using ESM Pro. This is a green fluorescent protein. It can already exhibit the green light. So a quick summary. The key idea inside this ESM Pro approach, we use importance sampling. That's another very familiar algorithm for NLP people. Inside expectation maximization, again, that's another algorithm we use a lot. We use the combinatorial features learned on the sequence and integrate that into the generation model. And this procedure is also a self-learning procedure. It doesn't require too much label data, lab collected data. So that's one advantage of the model. Okay, so going from sequence to structure, how can we use structure to better design a protein? So I'm going to focus on this one for using surface to design. Well, a protein, if you think about the protein as an object, it has a surface. So this is a SARS-CoV protein. So you can actually compute the outside contour or surface of the molecule. And this will be useful for certain application, for example, binder design. So if we want to design a protein that can bind to our target protein. So we have a target protein here, and we want to design another molecule that can bind to this one. Their surface should match, right? Their geometric shape should match. Then they can potentially be attached together. So this is a strong motivation why we can use surface to design. Of course, it's not just the geometry. On the surface, there are also some important chemical properties. For example, the charge, polarity, and also hydrophobicity. Those will either encourage or prevent molecule binding. So with that, we can design this model with the surface as an input. Here, it's actually chemical property augmented surface. We have a surface represented as a geometric shape. And on this surface, on each of the vertex of the surface, we have these properties, chemical properties. And then we design an encoder to encode this surface well into the embedding space. We get the embedding, And then once we have the embedding, we can use an autoregressive decoder. It's a transformer decoder to generate the protein sequence. So that's the overall framework. If you are curious about the surface, so how we get to the surface in training and at the inference time. So there's a tool called MS tool. It can convert protein data. It's from a protein data bank to point cloud. So we get the molecule surface representation. And there's vertices to indicate the 3D coordinates on the surface, and also additional chemical property associated with those vertices. There's not one-to-one mapping between the vertices and the residual. There can be many vertices for each residual on the protein sequence. And we also borrow some technique from computer graphics to represent the surface better. This is called surface smoothing. We use a particular technique called kernel smoothing, Gaussian kernel smoothing, to represent what originally we have some coarse-grained representation of the surface. Now with the Gaussian smoothing, we can represent more fine-grained details of the surface. But one issue of that is we get a lot more vertices. So if we just pass that to the encoder, it's computationally expensive. So we also do the surface compression to compress downsample this from this dense representation back into coarse representation. But this coarse representation will preserve all those tiny details. So at those detail part, we have more vertices, and those smooth part, we will have fewer vertices. Once we have this representation of the surface, we design two encoders. One is a local encoder to represent the individual vertices and the local geometries. And we also have a global encoder that will represent the correlation among all residuals and all vertices on the surface. And eventually, we have we use the multi-head attention, the same multi-head attention as we use in the BERT model and the GPT model, to represent the global representation and aggregate them, and then generate the sequence in the autoregressive decoder. Okay, well, how does it work? So this is one data set we evaluated. It includes the 6 categories of the binder design tasks. The first 3 are in the training. So these 3 are kind of supervised task. And these 3 are different tasks. They were not in training. So these are zero-shot directions. We want to extend the model into completely new tasks. But we are given the input surface for those tasks. And that's the average score of all these 6. And the y-axis is the, I think it's a success rate of the designed binder. So success rate is defined by whether the designed protein has a higher affinity score to our given target above the certain threshold. And again, so we find that this surface-based design is much more effective than earlier approach, like for example, this protein MPN that's inverse folding-based design. So if we are given the full geometry of the target protein and you just design based on that, then it's less effective. Okay, here's one specific example. If you are curious about the designed. So this is a designed protein, and they can actually bind pretty well. So a quick summary. So in this work, we use a geometry to guide the generation procedure. It's based on the surface geometry, surface structure, also based on the chemical property on the surface. And this proves effective in binder design. It's also effective in inverse folding. So if we are given the whole 3D geometry, we can also generate sequence as well. And it can also be used as an enzyme design. The enzyme, they are also important. Well, the surface is also important for enzyme design tasks. But we have a even better method for enzyme design. So that's the next topic I'm going to talk about, how we combine the two, how we combine the sequence and structure together to generate better proteins. So talking about enzyme, well, enzyme, they are biological catalysts. They can accelerate chemical reactions. For example, so you might be familiar with this particular enzyme. We have lactose, and this reaction, glucose and galactose. So if with the enzyme, we have this lactase. With the help of this one, we can better accelerate this reaction, because this enzyme actually reduces the energy needed to make the reaction happen. Okay, now the design task is for a specific chemical reaction, which we want to accelerate. Can we design the enzymes, we're talking about the protein enzymes, to accelerate that reaction? Well, how can we design? There are a few intuitions we get. So the first one is motivated by a prior work called impacting. So the idea is very familiar to our NLP people, actually. So they are taking a partial sequence as an input. So we have some partial sequence here. And we also get the structure of those partial sequence. So we get the 3D coordinates of those partial sequence. And once we have that, we are using this neural network to fill in the blanks on the sequence and in the structure. So we're predicting the sequence and the structure at the same time. So hopefully in this way, we can generate new proteins that has the same function as our partial sequence, where these partial sequence are actually mined from existing protein family with the exact same function. So these partial sequences are called functionally important sites, and they can be automatically mined from the dataset. So that's the first motivation. The second motivation is similar to multilingual machine translation, where we use this language tag to indicate the translation direction. And then to tell the model, okay, this time you need to translate from English to German. And then next time you can translate from Spanish to Chinese. And hopefully by training this multilingual model together, you can generalize the translation capability of this model to new languages that you have never seen during training time. Well, we want to do the same thing for protein design. So for this purpose, we use a protein family tags. So this is enzyme tags that can tell the function of a particular enzyme. So there's a specific database called Brenda database. It has organized tree at 4 levels to tell the functions of these enzyme categories. For example, this is a one particular 1.1.1.1. So this is a alcohol dehydrogenase. So this is one particular enzyme, and we can use this tag as an indicator for the function. And the hope is so at training time, we train for that, and at test time, inference time, we can generalize that from the tag. Another motivation is specific to protein and enzyme. So for many enzymes, to make it work, it has to use some substrates. These are small molecules that can help the catalytic function in chemical reactions. And this protein has to bind to this substrate. And each particular reaction, each particular enzyme has a unique set of substrate to be binded. So these are substrate specific. And when we design this enzyme, we want to design this enzyme that can bind to the substrate, so that at reaction time, it can bind further with our product to produce a final chemical compound. We can combine all these 3 ideas together to design the model. So this year we proposed this model called Enzygen. Overall, the overall architecture actually has 3 elements. We have the sequence representation here. The sequence representation also include the tags. So we have the enzyme tags to indicate the function. And we have coordinates of those residues on the sequence. And in addition, well, I will talk about the other component, but how we train this. So we use the same idea as in BERT. We mask some portions of the sequence and along with their coordinates. And through this model, our design model called NAEL, this neighborhood attentive equivalent layer. So through this model, it's trying to recover the residues, those masked residues, as well as their coordinates, their masked coordinates. And hopefully this model could predict those missing pieces. And this is a more detailed model architecture, but I will skip the details here. Well, in the learning, we combine one additional piece here. Now we mentioned this enzyme should be substrate specific. So we have a substrate molecule here. Again, it's a graph. We use the same network, it's a neighborhood equivalent layer, to represent this molecule. And we get the representation of this one. And at training time, we are training this enzyme and substrate interaction score. We have some additional label data for that, so we can introduce additional training laws just to encourage this protein sequence to bind specifically to a particular substrate. Okay. Well, one more important piece. How can we discover this functionally important site? We can mine them from the data set. Well, suppose we have, let's say we have 5 sequences here from our database. We first align them using multi-sequence alignment algorithm. And then we find the common sites. In this case, we find that well, on this and this and this, these 3 sites, they are common across all the sequences. So these sites are functionally important for this particular category. And then we can do that for each of the category. For each category, we find a different set of functionally important sites. And at inference time, once we know which category we are going to generate, then we will give this automatically mined functionally important sites as the input to guide the generation. Okay, well, to train the model, we also build a data set called enzyme bench. It includes 100,000 entries, 100,000 proteins from the protein data bank. It's corresponding to 3,000 enzyme categories, fourth level categories. So it's pretty comprehensive. Of course, the whole data set actually contains 8,000, but we eliminate those categories with too few enzymes in it during training, but it doesn't help too much. And then we mine those functional importance for each of these 3,000 classes, and we merge them into about 256 third level categories. And we test on 30 largest categories on the third level. And we split, we split 50 for validation and 50 for testing. So those validation and testing, they are not in our training. Okay, so here's a result. This one shows the enzyme substrate binding score, interaction score. It's called ESP score. So it's an indicator to tell the affinity between the enzyme and the substrate. The higher, the better. And these are a few examples. Example enzyme categories we put here. There are 30 of them. The rest are in our paper. And this is the average score for all the methods. A little bit introduction of the other methods is proceed and IF, well, in particular this one, IF diffusion and the inverse folding. This was published earlier in Nature, I think, last year, using inverse folding and the diffusion algorithm. This ESM2, which we just introduced, this is a BERT-style model. Well, itself, it's not enough. We need to add the EGN, that's the equivalent graph neural network, to predict. Well, in terms of the stability of the protein, when we design new proteins, not every protein sequence are good. They should fold into a stable structure to be a valid protein. So there's a score called PLDDT that's computed from AlphaFold. In this case, AlphaFold 2. It will give a score that will tell how likely this protein sequence will fold into a stable structure. And there's a generally recognized rule. So if this score, PLDD score, is above 80, so that means the structure is stable. So we also evaluate this PLDDT score for all these categories. And on average, this enzyme will generate proteins with much higher PLDDT score. That's higher than above the 80 threshold. And here are two cases we generated using this model. I can't fully explain every details, but I can try. So this is one particular enzyme we designed for the shikimate kinesis. So it's an enzyme that uses ATP as a substrate. And here's the ATP here. This is a small molecule. So that's a substrate. And this green part is our designed enzyme. And so we can actually visualize binding here. So there, well, at least from the illustration, so there's a strong binding between this substrate and our desired protein. Okay. So a quick summary of this model. So we developed this unified model. That's one single model. For these 3,000 enzyme families, we are pretty much using similar idea we developed for multilingual machine translation. Of course, we have additional guidance. We have functionally important sites that's automatically mined from the database. We have enzyme category tags to tell the function of the protein. And by combining this sequence and the structure all together, we can design better proteins because function and the structure are strongly correlated. And we also take the substrate binding into the training time. We don't use this. We didn't use this substrate at inference time, although we can add that as well. So well, one-page summary of the similarity and the difference between generating language and the molecules. In terms of distribution of the data, so we have this sequence. We can use BERT and GPT to model the distribution of discrete sequence. For protein and molecule, we have ESM and ProGen. They are pretty much similar. For 2D structure, discrete structure, there was a tree STM, and there's MPNN for molecules as well. That's message passing neural network. For 3D geometry, for a continuous structure, well, we don't have anything for the language. That's different. So for that purpose, for molecule, we have EGN, equivalent neural network. We have Enzyme, we have Pro. All this taken care of the 3D geometries. For the generation, for the decoding, to actually decode the molecules and text, well, there's score-based method for both language and the molecule. There's conditional VAE that was quite popular before GPT. And there's ESM Pro. This is also score-guided generation. And there's also editing-based approach. That's iterative editing. So we're not just doing a single shot generation. We're generating one candidate and then we keep improving it. So there was, for example, CGMH approach that keeps editing the text. And similarly, there's mass and molecule editor 3D algorithm to keep editing the molecule and to get better and better molecules at the inference time. Some important takeaways for molecule design. The problem formulation is important. Of course, we can borrow a lot of the ideas from natural language or from computer vision, from computer graphics, but we still need to consider the chemical, biological specific information. This guiding information is important. For example, the fitness score tailored for a particular chemical reaction, the chemical properties, the molecule categories, tags, motifs. And modeling the structure and geometry is critical for molecules. Keeping this equivariance is explicit can essentially, it's augmenting our training data, so we can use much less data to train our model. And it's also important to model the mutual constraints between the sequence and the structure so that we can design this structure consistent with our sequence. And the interaction between multiple molecules. Usually in real applications, we are designing a target molecule that will be effective in a complex, in a molecule complex. So we want to model such complex so that we can design better molecule to be useful in the practical applications. Okay, if you are interested in more details, you are welcome to read the papers I mentioned in this talk. Thank you.
We have time for a few questions.
Yeah, so in sequence generation, it seems that the fitness score is critically important. Where do these fitness scores come from?
That's an excellent question. These fitness scores are separately train the model on lab collected data. For example, for the green fluorescent protein case, we already have discovered several hundred of these protein sequences in that category. And then we train a BERT-style model to tell the score, the fitness score for that particular category. And we have to do that for every category where we want to generate. So that's actually one limitation of this score-based approach, because you need to have a set of lab collected data to train such fitness score. And if we are designing molecules for new category, like new enzyme functions, that there's no natural protein with this function in nature, then it's actually impossible to make it work. And that's why we have to use additional information, such as the geometry, substrate, additional information to train the generative model.
Thank you for the talk. My question is, how can you ensure the diversity of your generated proteins, especially your first paper? I think it's just on baseline or cheaper than that. I know that their motivation is to ensure the diversity. And this is by sampling from energy-based models. And I sort of discovered results through that new method is even better than cheaper than. So I'm trying to understand what is the source of improvement in your method for the diversity.
Okay, excellent question. So the question is about the diversity of the generation. Well, we have the same issue in language generation, so we have the here similar issue in molecule generation. In language generation, how we encourage diversity, well, there are different ways, but one most effective way, well, I should say, is through this generation from the latent space. In particular, using this VAE model, variational autoencoder. If we have latent space and we are sampling from the latent space and then generating from that, usually will lead to higher diversity. So the diversity is okay here for this model. The issue here is how can we ensure the generated sequence has the desired property. In text case, maybe we want a certain particular style of the generation. In molecule case, we want a particular function. So that's difficult. And that's why here we have additional scoring function to guide the generation. This is well, in contrast, so some of the model might not produce very diverse sequence. In particular, for example, for ESM. ESM, if you remember, this is similar to BERT. So in BERT style, it's not actually a generative model, but you can use it for generation purpose. So you can kind of mask it and generate the masked portion, and then repeating this procedure. And hopefully you can generate better. And the diversity is dependent how much you mask. If you mask, let's say, 90% of that and just generate completely the rest, it might lead to very diverse generation. But then on the other hand, it won't produce high quality sequences. So there's a trade-off between this diversity and quality. And in our case, we train our generation model, like proposal model. We have a variational model here to approximate these high quality ones. And while still this one will have the diversity because itself it's also a variational autoencoder. So it's generated from the latent space. It has that diversity and also the high quality.
We have time for 2 more questions.
thank you for the presentation. Neil was here curious about protein generation. I was rather more interested in the safety of the protein generated by the model. Like, for example, in like some diseases, like for example, in is caused by protein, but it has a normal structure, but exactly the same amino acid sequence to the normal, which doesn't cause the disease. So I was wondering if the generated protein might cause. I was wondering how to evaluate the safety of the generated protein.
Okay, so the question is about the safety of the generated molecule, let's say. Well, safety in this case can mean different things. For example, in drug design, safety is probably toxicity to human body. For that purpose, we can actually do that in this framework. So this is one example to do that, but there are other approaches as well. So we want to generate the molecule satisfying certain property, and these property are represented as a scoring function. And we can have multiple scoring function as the objective, just multiply them or properly calibrate and then multiply them. And then once you have that, we can use this framework called MCMC, Markov chain Monte Carlo approach, trying to iteratively optimize for that property. And that score can include one particular score for the toxicity. So we can separately train a toxicity prediction model. Of course, it's itself is a challenging problem because there's no very accurate toxicity prediction model yet. But we can use some proxy for that purpose. It's pretty much similar to our text generation case, where we want the generated text to be fluent, to be natural, and to be beautiful, maybe to be creative, to be interesting as well. So if we want to satisfy and to be non-toxic as well, so to satisfy all these properties, we can combine like scoring function for each one, and then for overall joint objective.
Time for one more question. Going once, twice. Let's thank our speaker.
Thank you.